All right, hello and welcome. This is Celestial Theodolite update number 22. Tonight we're going to be going over some math in relation to how everything is derived behind the scenes on the Celestial Theodolite and what has been uncovered in relation to how globe geometry works. So we're going to be going over that math, and then Goose is going to be going over a simulator where he puts meaning to the math so we can kind of see the visualization of what it looks like, because looking at notation on paper doesn't really quite sell it always. So Mike, whenever you are ready, good sir, if you got your PDF available.
Okay, here's my PDF, um, and I just posted this to Livestream One Text, the PDF for anybody who's interested in having a copy of this. Uh, and I wrote this just for the people who may still be having trouble understanding um, math involved. I'll enlarge that a little bit. So to start with, I recommend the NOAA site that Jesse recommended to us many months ago to get very precise distances for anybody who wants to be ultra precise. Um, and the precision makes a difference. It's usually on the order of meters of height or arc seconds of um, angles. But if that's important to you, use the NOAA site to get your distances between any 2 points. And then something is very important if you want to try to reconcile topographical plane math with globe math. You need to know the distance angles, theta sub d, and that's easy to calculate. It's just 360 degrees times the distance divided 2 pi r. And if you want to be ultra precise on that, there's sites that give you ultra precise distance for locations on Earth. Or you can just use 6371 kilometers, which is a close enough approximation for most cases when you're trying to reconcile globe math and topographical plane math. So next, you need to know the altitude of the mountain peak, and I recommend getting that from the official peak website. So uh, almost every city with a peak near them has an official website for that peak that gives you all the stats for the peak, and that's the absolute best place to get the um, official peak altitude. A pretty good alternate if you can tolerate uh, small amounts of error is a topographical map, and you can get the altitude of the observer from either GPS coordinates, which is the most accurate way, or get that also from a topographical map. And then you want to calculate the rise of the peak, which is just the peak altitude minus the observer altitude, and that's the rise of the peak. So it's pretty simple. Next, you want to calculate the apparent rise of the peak, which is in stellarium that sorry, not in stellarium, but in globe Earth, that would be called the corrected rise. So there they take the actual rise and they subtract d squared over 2r, and that's supposed to compensate for the alleged curvature of the Earth. And you also, another very important factor is you want to calculate the uncorrected rise of the peak. And that is, if you compare it to the apparent rise, it looks very similar, but the difference is it's 2 times d squared over 2r. And so if you note, it's subtracting d squared over r instead of d squared over 2r. And that's the different distance stellarium will tell you is the uncorrected elevation to the star. And um, for each occlusion, each emergence, depending on which way you're going, you want to determine the geometric heights, so the height of the peak, the rise of the peak, which is the distance times the tangent of theta sub p, and the observed rise, which is the distance times the tangent of whatever angle stellarium reports, depending on whether you're measuring that from the observer's location or from the peak. And I give you equations right after that of how to calculate the difference in rise between what rise over run tells you it should be versus what you observed by timing occlusions. And what a lot of people don't seem to completely understand yet is that's a common discrepancy that affects both globe Earth measurements and flat Earth measurements via this celestial theodolite. So what delta H really does is it corrects for celestial refraction, altitude errors, distance errors, timing errors, and numerous other factors that cause height discrepancies. And a few people have looked into, they try to categorize each of those things, which you can do by measurements and calculating what the theoretical refraction should be. So anybody who's interested, that's a useful number. Now, at this point, you have enough information to be able to find the flat angle, which is just the arctangent of rise over the run. And when you want to account for that height discrepancy, you can do that by, instead of finding the rise or the run, you find the calculated peak altitude, which is the altitude peak minus the altitude observer, and add to that delta H, divide that quantity by the distance, take the arctangent of that, and that gives you the flat angle. The globe angle is somewhat similar to that, where you just take the arctangent of the globe estimated rise. That's the one that's minus e squared over r divided by the distance. Or an alternate way of doing that one is the stellarium reported angle, uncorrected angle from the globe, plus the delta H, divide that quantity by d and take the arctangent, and now you've got the globe angle. You might also um, let me rephrase this. The important thing to, I think, an important thing to realize is, due to the central angle theorem, if the Earth were a globe, the angle from a distant observer to a peak must be exactly half the angle traversed by stars between those same 2 points. And I give you a website you can play around with if you don't already understand that. If you ask artificial intelligence, it'll tell you, oh, that doesn't apply to a sphere. But excuse me, I call it artificial intelligence. It's actually automated indoctrination. People who are actually intelligent and can think for themselves realize it most certainly does apply to a sphere as well as to a circle, because of the great circle that intersects 2 points on a sphere. And you may have to think about that, and I won't necessarily justify that position, because this is something you need if you want to do globe math, but you don't need any of this crap to do flat Earth map. Um, and an important takeaway, and this is, I think, what that most people hang up on, is the fact that the globe angle equals the flat Earth angle minus the distance angle. And that angle, the globe angle, is always much too low for any given star that you're seeing occluded from any observation point. And because it's much too low, it's necessary for people trying to calculate globe angles to add half of that distance back. And they mistake that for celestial refraction. In reality, that's just creating the illusion that there is a globe, which wouldn't otherwise be there, and it isn't there when you're doing straight flat Earth math. It's you only have to deal with that when you're trying to apply stellarium angles to a globe, and that 1/2 of the distance angle is essential to lift the stars up to the point where the mountain peak can actually occlude them. Because when you calculate those angles, you'll always find this way below the peak, and that star should have disappeared long ago. So we have to pretend that celestial refraction is lifting it to the point where it just now disappeared, right at the point where the flat Earth told you it would disappear, rather than much earlier when much later when the globe Earth told you it should have uh, occluded. So it's a very, very clever deception, but that's not the same as the central angle uh, theorem that says that the central angle is subtended by 2 points in a circle, and that's twice the inscribed angle subtended by the same 2 points. And go to the website if you've never played around with that, you don't understand that concept. Um, and then I'll skip my little statement there about the Great Circle, because I really already mentioned that. But the final takeaway is you're going to find that what our Glober's friends call the apparent angle is actually their globe angle plus 1/2 of the distance angle, and that's the angle that allegedly appears to be um, the location of an occluded star, and that's also the same angle that terrestrial Theodolite allegedly measures. And um, for flat Earth, sorry, that's the celestial part of it. The terrestrial part of it, that same angle is the globe angle plus 1/2 the distance. So what you see is for stars, you're taking the globe angle, adding 1/2 the distance. For terrestrial measurements, you're taking the globe angle, adding 1/2 the distance. An alternate way to calculate the terrestrial angle is the flat Earth angle minus 1/2 the distance angle. So you can do it either way. Um, the important thing to understand is everybody who believes in a globe desperately needs the apparent angle to be true. It's a fantasy. It's not real. Only the flat angle is real. That's the one we measure with the celestial theodolite. That's the one plane trigonometry tells you should be the angle you get from the rise or the run. Everything else is adding or subtracting an alleged curvature of the Earth indicated angle. So that's just a summary for people who don't understand it yet. And um, this may come up later in the presentation, and that's why I'm presenting this now. That's all I
Nice.
have to say about this.
Thank you for the recap. So like some of this is, very abstract, doesn't make any sense. But like I said, Goose is gonna show us he's gonna walk us through a simulator, giving meaning to all of the equations. Goose, whenever you are ready, good sir.
Sounds good. Hold on. Find the right screen. Now where to go? Oh, I know. Doesn't like it when it's full screen.
Oh yeah, the classic.
Oops, that's the wrong one.
All right, you have shared your Discord, sir.
Just for old time's sakes, hold on. Okay, share your screen. Oh, come on, go away. Okay, there we go. All right, you guys see that?
Yes.
All right, so this guy here, this is Pike's Peak, basically. So I'm just pulling the values out of Alan's spreadsheet here. Pike's Peak, 39 aquarii. The distance, the observer height, the distance from the observer to the peak, temperature. Here's where you enter the true star to the peak. So 233, 22.32 seconds. 2 degrees, 33 minutes, 22.32 seconds. And then you can enter the true star position from the observer. So 2 degrees, 6 minutes, and 8.6 seconds. So basically what I've done is just put Mike's math into Desmos form here.
So you're setting up the variables to match what his notations are supposed to represent, right?
Yeah, I tried to match his variable notation as closely as possible, so it's easy to follow along, so it's easy to follow along with the document, and it's all in order too. So
gotcha. Okay, so theta star theta star angle observer is the true position of the star at the observer location, and then like theta star angle peak would be with respect to the peak's location. So we're just notating. So we're just recreating all the math that's going to be done. We're just assigning the numeric values to the variables.
Exactly. Yeah. Just to give like some kind of real world example to plug into the math.
Gotcha. Okay. So theta Bennett would be our astronomical refraction.
Yeah. I've got another. I think I've got however you pronounce it, Seinhauser refraction in here as well.
Oh, nice. That's one of my favorites.
Yeah. Basically it just starts right here. Topographical plane math for celestial theodolites. We do the distance because we enter it into kilometers. You got to convert it to meters. Everything on the graph is in meters. We got our radius value, which is Earth radius in meters. Is that number there? 6 million. And then here is our distance as an angle formula.
It's the central angle theorem there.
Yep. And then we go down to, so this is AP is our peak elevation, and then A0 is our observer height. And here we're just taking the delta between those two. And we're going to do our globe predictions here. So 227. Let's see if we click on here. I'll zoom in a bit more. Yeah, 227, right? Oops, lost it. Anyway, 227 is the peak there. And then we'll do and then this is the globe calculations here. So we got, this is the apparent peak height. And that's observer height mountain peak height minus observer height.
Oh, that's fantastic. So on the bottom there, you've got a curved line, and this is representing our globe with drop over distance relative to this 50,000 meter distance. And then so the dark gray peak is the globe, apparent peak, or no, well, we say apparent, but that's the physical elevation, accounting for the drop over distance to the peak, making it physically lower. So, and then
Yeah.
and then the one above it is the flat baseline with no deviation. So it's dude, that's a nice, very nice.
Yeah, I even got it so it was kind of angled ever so slightly. I don't know if you can see that, but
Yes, yeah, I appreciate the angle. That's awesome, dude. So
that always bugged me for the very beginning.
so real quick, if you zoom out, can you give the people a the observer eye view there of what's going on? So we got an observer standing on a globe and or a flat Earth at the tangent there where they would both intersect, and then as the distance goes on, we see the mountain on Earth curve. So we saw the zoomed in version where it was lower than the flat baseline where there's no deviation, and then as you zoom in there, you can kind of see as it extends out, it's just a continual flat baseline. And then the celestial sphere is going to be the movement of the stars and are, represented by our vision. Whereas if you were standing on the ground, the same thing would be created by the ground geometry. So very, very cool, Goose. And what was the radius that you used for that celestial sphere there, Big Dog?
I think it was like 10,000 kilometers or something. Let's see, where is it?
Isn't that like 6218 statute miles or whatever?
Yeah, what was it? It was, 10,000 kilometers. This is the exosphere and the celestial sphere.
Right. So the literal, so and to keep in mind, 10 million meters is from the North Pole to the equator, and 1 meter is a ratio of that. So it's, or what is it, 110 billionth of that. So it's literally the exact equivalent there. The purpose of this is showing that, if we have a radius of vision that shows the same thing over this distance given, it's going to create the same exact thing, perception wise. Now they could be, further out or a little closer or whatever, but the effect is going to be the exact same thing within that range. So it doesn't matter, like when they're like, oh, but the star is actually, X amount of light years away, doesn't matter at all. When you're trying to navigate or calculate distances between longitude lines and all that, when you're referencing the stars, this distance is as far as you would need to go. So anyway, go ahead and continue. I just wanted to show what we were actually looking at there.
Yeah, no, that's good. Yeah, I forgot to give like the bird's eye view of the whole thing at once. And then, I think for the exosphere, I picked that value because that was where like the atmosphere begins or something like that. And then you independently discovered it was also the celestial sphere radius, which was kind of interesting. And then and then also I call this like down here is like the physical globe, and then here is like the conceptual globe. Like this is the one that they use when you see this Earth radius here. This is the one that they use for navigation.
My man. Go ahead and zoom back in there. Let's take a look at that peak.
And we also have an observer. Oh, where is she?
Dude, who is that? Who's making this observation?
She's to scale. I wish you could zoom faster on this. She's there. Where'd she go? She's gone.
Oh no, she's not there.
Where'd Nikki go? I'll put her back. She'll be back. Anyways. Let's get back to the mountain. So here we are back to Pikes Peak. So we have our flat Earth Pikes Peak, and we have our GE globe Earth Pikes Peak. And so here's this guy is where the true star has been measured at the peak. And then we can turn on this line here, and this is where the globe says the true star is. And that's just calculated straight, like these the star angle peak is like straight out of stellarium, and then star angle observer is the true star with atmosphere off out of stellarium. And here, this is where we start to calculate our deviations. This is what Mike was talking about, where the deviations are the same for both the globe and the flat Earth. So they're both around 40 meters. Once you like that, once you take out like the celestial refraction, celestial refraction, distance errors, timing errors, and any other factors that, if there's a tree or something like that on there, maybe that'll mess you up. And then when you correct for all of that, or subtract out the errors, you get your corrected true star positions. On flat Earth, it just hits the peak here. On globe, where we end up a little low there. So what you'll see is when you do your calculations, your true star position is low, and then you need to raise it up by this
Little
half
by
that distance angle.
Yeah, so this is really important here, because this is what we're going to find is like this is going to be their astronomical refraction correction, right?
Yeah, in quite a few cases. There's
Right.
sometimes their refraction thing will overcorrect or undercorrect, but
Right, but it has to be at least that amount to compensate, like geometrically.
yeah,
Which is the important part. So what we're going to see is like for every formula, it's basically 1-to-1 compensating for the would-be drop over distance.
Yeah, exactly. And where this true star position is coming from is from that central angle theorem. That's like it's a geometrical like proof, right? Like you can't really get away from it. And then and that's basically it. Like so you can go in there and you can play around with these values. You can put in different peaks and see what they look like. Yeah, that's it. Yeah, and like I should post a stick a I'll put something in live chat if I can figure out how to do that. Yeah, I'll post this in chat, and then people can play around with it.
Awesome, thank you, Goose. So yeah, just giving some representation. Oh, you got some central angle for us?
Yeah, there's an angle theorem.
Nice.
I'm not sure. It might be broken at the moment. I'll fix that and post and repost that. And then you can also do some fun stuff like you can construct a globe from the raw flat Earth measurements. You can bring yourself back to a plane just using the flat Earth measurements. You can get yourself all the way down to planar, 90 degrees planar. Yeah. That is the simulator. Something to play around with if you're so inclined.
Fantastic work, man. Great representation. All right, we'll do some open Q&A, and then we'll wrap up. I just wanted to show that. I thought it was really cool and really pivotal to getting a grasp on what all those notations means when you see theta sub d equals 360 times, like what are you doing? What does that mean, right? Like I could never figure that out. So it was only after going through all this and seeing it visually and stuff like that I was able to make any sense of it. And so anyway, this is a good tool to put the concept to visuals. Shane, did you have anything you wanted to add on what's going on here? Or are you arguing with nerds in the chat?
Yep. Nope. Definitely in the chat.
No worries.
Dude, we should bring in Roland my boulder and get him to go through it though, if we want some honest interaction, maybe.
Nice. All right. Well, if there are no questions or comments, we'll go ahead and wrap up. Tonight was a quick night. Or was that guy going to come on? Did you say, or was it just like a hypothetical?
No, I was hoping to pressure him to open his mic so he.
Oh, I got you.
Now,
He's not in the voice chat. All right.
Roland my boulder is definitely in the voice chat. He's right here. I'm looking at him.
I don't roll him. If he was in the voice chat, his mic would be talking though, wouldn't it? Would be.
I heard it. I can hear him. Yeah, he's here. Is this going to turn into a Riggs moment? Just sit in awkward silence?
Yeah, if Boulder's not here, we can go ahead and wrap. To answer your question, Coco, about the recap for the beginning thing, I want to put together some nice visuals and slides to go over everything. So to start fresh for like people that don't know the trig and all that. So I haven't done that yet, but I did write like an introduction to the thing. If you want to read that. Oh, nice. Word. Okay, so Rolling Boulder is going to come through next week. Very nice. And there's the Theo introduction thing that kind of goes over the concepts of it.
Can you not hear the other guy talking? He's trying to ask you a question.
Was Left Lane talking?
Who's that?
Left Lane. You don't hear him?
I haven't heard Left Lane in years, bro.
You have everybody asking you
Yeah,
questions.
he's got me turned down because he has them hard questions he don't like to answer.
No, I got you turned down because we were going over Mickelson Morley one time, and you said that they disproved the ether. So we pulled up the paper to read directly from it, so we could quote from it. And what you said wasn't in there at all. And we went over what I said was in there, and everything was in there. So I never talked to you again because you'll just be contentious to be contentious.
Whatever.
Anyway, what was your hard question, sir? Go ahead.
I said, why can't you just do simple trig with A being the distance to the mountain, B being the elevation minus the observer's elevation, and of course the hypotenuse, and take the angle at C and A.
Did you not see the what? That's what we do. You talking about rise over run, my dude?
Just described our method of.
You
No,
just-
just do a simple trig and see what is the angle on simple
Yeah.
trigonometry without all the other stuff.
That's the
Bro,
whole premise
that-
of
that's
the whole
our-
thing. That's what we've been doing. Thank you so much for shutting it out, man. I appreciate it.
That was really tough to answer. Thank you.
Well, it actually like that's what we keep trying to bring everyone back to specifically, and that's what everyone keeps diving and dodging away from. Is that when you use basic trig and you just account for Earth curve, it ain't there. The star never aligns where the geometric Earth curve should put it, ever, not once. And that's how we bring in all the other factors of corrections of refraction, celestial and terrestrial. How we went through all of that form-fitting curves. That's how all that gets brought in, and still doesn't save you from the failure of the raw geometric trigonometric prediction from the beginning.
Not assuming curve, assuming flat. Assume it's flat, simple trigonometry. What would that angle be?
Yeah, that's our whole
Every
premise.
time, yeah.
Well, what is it? What is the angle on the Pikes Peak with just simple trig?
231.
231.
Two minutes, 2.5 minutes.
2 degrees, 31
minutes.
minutes. Jinx or whatever?
we know Pikes Peak pretty well. That's the flagship example.
You guys don't have Pikes Peak tattoos or whatever?
Like 201 meters a globe drop over 50.7 kilometers. Like it's a 202 meter difference in height. That's what we're trying to account for in our prediction. The actual difference between flat and globe over that distance. We're trying to account for a 202 meter drop differential, and we're trying to account for it in the angle at which the star gets occluded by the mountain. It's the most basic like distillment of the process. I like how your question was like, why don't you just do that?
Yeah, but the thing is, I thought that the original sighting he did, I think his brother may have did with his Theodolite was not 2.5 minutes. Or two and a half degrees.
What does that have to do with using plain trig to make the prediction? You're kind of changing subjects to a different thing. The optical
But it's
angle
not
is
agreeing.
the optical angle is what's in dispute, though. Like we're not saying that you can't look through a theodolite and get a measurement of 217 for that mountain peak. We're saying that is due to optical reasons, whereas the globe lads say that that's due to the physical drop over distance, thus making the physical elevation of the mountain lower. So the celestial theodolite compares the difference because when the star traverses the central angle sweep of that distance between you, basically when it traverses that angle in the sky, it's going to be either at 231 or 206, depending on the occlusion timing. So when the occlusion occurs, we reference where that star is at the end of its sweep, and if it's closer to our angle, then that means that there was no drop over distance for that mountain peak. So simply referencing an optical theodolite measurement isn't enough to falsify the null hypothesis or tell us anything unique about where we live if our premise is that there's an optical equivalence for what you would call curvature.
It's also confusing like normal theodolite measurements in optics and refraction with the actual theodolite, celestial theodolite process that we keep going over, which is based on occlusion timings only, right? And that's how we get our differential. Our prediction angle is based off of that occlusion angle. That's the whole prediction. As Ruhif has confirmed, as I use his diagrams to show the principle now. So that kind of cuts the corner when people are like, oh, you're starmen in the globe. And it's like, well, here's the globe giving us our numbers, and they're all the same numbers that we got. So that's why we have Pikes Peak. You have 217 is the globe prediction. 219 if you add terrestrial refraction, which we usually don't allow, still is not close to the actual occlusion time of 232. 231 is much, much closer. That's how the whole process works every time.
Left Lane, did you want to respond? Hold on, bro. Did you want to respond?
No, they answered. And, I don't know. And I'll have to. I don't know. It just sounds like a whole bunch of information that we could just answer the question, make the observation, see what the angle is, see what it should be, just writing it out on paper and see what the difference is.
But you understand the difference between calculating it and getting the actual timing versus just doing the optics, and why there's a discrepancy there?
Well, my question doesn't involve any star occlusion or timing. It's just the elevation of, the angular elevation of Pikes Peak from that observation point.
All right. Was there anyone else, or do I inadvertently have somebody else muted?
Yeah, I think Robert was asking. He asked, "Are the stars moving straight lines?" Is what he asked.
No. They're traveling in a circle parallel to the ground. We perceive them arc across the sky, and like that arcing is what causes them to get lower as they get further away in their circle above us.
So if they're arcing, why don't they push southwards and approach the horizon and then come back up?
If they're, I don't know what you mean.
Yes, if you look at a circle on top of a piece of paper, right? The arc of it pushes to a side of the paper and then comes back around, right? So the stars should be going lower on the horizon as they're traveling through the sky. South, they should be going south and then coming back up.
Yeah, I'm
I get
not
what you're asking, bro.
not sure.
Well, I mean, in terms of just going back, if there's not much with that, but left lane, I mean, dude, obviously, like they're referring to the difference between just optically looking at the mountain with a theodolite over distance, and obviously the claim is like, is that due to our optics, the reason why it looks like it does with the theodolite over long distance versus Earth curve? So do you understand the difference between actually getting the timing, and once you actually get the timing, you're getting like I like that term, like an internal timing, like you're getting an internal timing data point of when the star is actually physically occluded. You see how that's different because you're actually using the timing of how it aligns with the geometry of the ground versus just looking at optics and trying to make a conclusion about the shape of the Earth based on extremely long range optics?
Well, I mean, the timing part in the star occlusion, I mean, it's all, with me driving all the time, I can actually write this stuff down and do the calculations and all that stuff. So I mean, that's my main question is what's the difference in the straight trig on a flat surface and what you actually observe? What's the difference in those two? And then that's where my question would lie.
Yeah, so if the planar trig matches with the timing of in terms of the planar trig matches the timing, what would that reveal to you? If the timing actually matches the plane geometry.
Oh, the timing, I mean, of course, timing involves when is the star going to be occluded. I'm not even talking about the star being occluded.
Well,
Right, but I am talking about it.
Yeah, time equals angle. So if we know when it was occluded, we know what angle it was at, and we could see where it was at relative to the peak versus relative to the observer, and we could do the comparison. Because, like I said, the star on a flat Earth or a globe still has to traverse that same arc in the sky. So we want to know when it traversed that arc at the end of it, and it gets occluded, is it getting occluded at an angle that corresponds to a mountain peak that has no drop over distance or one that has drop over distance?
And so what did you get?
So for Pikes Peak, the star got occluded at 233. That's where the true position was with respect to the peak. And for the globe, they predicted, or the position is at 206. So if you take the intersection difference between the two predictions, we're 2 arc seconds off, and the globe, based off of their drop over distance, is 10 arc seconds off.
Yeah, there's no drop over distance on globe.
Come again?
There are no drop over distance.
There's no drop over distance on a globe. Is that what you said?
Yeah, there's no drop over distance.
All right, word.
All right.
There's
I mean,
there's
with respect to a mountain's height as measured from the distance, depending on how you look at it, you could definitely say that. I would say
yeah,
that's a lot of ways that we determine that. I believe in my mind, the Earth is a globe. You can see basically a mountain in the distance that you shouldn't be able to see, and the one in the foreground is measurably higher.
yeah, it's angle. It's
Well,
angle. There's
by
no
any
drop.
by any Earth curve formula known to man,
Yeah,
it
my
comes out to a
dude.
difference of 201 meters.
Yeah,
So,
my
like,
man just said there's no drop over distance on a globe, so like I don't know where to go from there on that. But the point is, if there's no if there's no way to substantiate geometric drop on a globe, then I'm going to go ahead and conclude that there is no curvature. Then
There's no such thing as drop. It's called angle. Angle.
yeah, that angle also converts to a distance. Like that was actually covered heavily in the beginning of this presentation. Because
No,
actually,
when you say
because how we get the drop over distance, it's actually the drop over distance is half of gamma, and gamma is the central angle sweep. So let's say let's say the central angle between Pike's Peak and the observer is 27 arc minutes. Half of that is 13.5 arc minutes. That's going to be the drop over distance. You can do a tangent to convert that 13 arc minutes over that distance to convert it to 200 meters of drop. You subtract that 200 meters from the physical known elevation, and that's what the drop over distance for that peak is. If you disagree with that, then you have a different conceptualization of globe geometry, and we can't continue a fruitful conversation.
What is it if you do it in just pure without the arc seconds, just like a degree? What would it be in terms of a degree?
13 arc minutes. So you would take
Like point
oh,
0.000.
I'm sorry. The amount that half gamma for the central angle would be 13 arc minutes. So you would subtract that from the flat Earth angle. That would give you 2 degrees and 16 arc minutes for a raw geometric globe for the mountain peak.
2 degrees and what?
16 arc minutes.
16 arc. Do you know the conversion from arc minutes to just a raw angle? Or no, if you don't off the top of your head,
you want the decimal degrees? It's 220,
like
2.28. 2.28.
2.28. Okay, so that's what that's what you said the true measured, like as you measured it basically on the day was?
So no, that's the prediction for what the physical elevation of the mountain peak is relative to an observer that is 50,000 meters away.
Okay. And you said the difference between the two, the globe prediction, and basically what I'm asking is for a raw number for the difference between the globe and the flat prediction. Like, do you know that off the top of your head?
I sure
I
do.
mean, you probably do if you've been working with ARC.
I'm sure do. If you pull up, I just started a live stream, so we can go over it right here on the spreadsheet.
Okay, I'll take a look at it.
All right, let me know when you're in, and I'll walk you through these. Okay. All right, so we got the rise over run for the peak over here. This would be the flat Earth prediction. So this comes out to the decimal degrees on this is 2.51, and then the drop over distance is 0.23, which comes out to be 13 arc minutes, which comes out to be 202 meters. And then when you subtract that from the flat Earth angle, you get 2.28, which converts to 2 degrees 16 arc minutes, or 2,024 meters. So the difference in elevation there comes out to be 203 meters difference in elevation, or 202 actually. This is a rounding error. Anyway, it's
can you convert that to, can you make like a box like on I and convert that to like a raw decimal?
what are you trying to establish?
I don't. What do you? For what purpose?
It would just, it's in my mind, it's a lot for me to like grasp the distances you're talking about, to know like how large and how small they are. The arc minutes seconds kind of fucks with my head a little bit, and if I have like a raw decimal, I can visualize it a lot better, and I think a lot of people can as well.
So
Visualize raw decimals, is that what you're saying?
The decimal degrees are right here. So 0.18 or
okay.
So 2.28 is what the globe predicts for the elevation of the mountain peak.
That doesn't seem precise enough, though. Wouldn't the degrees, minutes, seconds have a lot more significant figures on it than that? Than just 3
Oh,
significant figures,
I have it.
right?
I have it to
It's
only.
only
You want
showing
you want to
2
show
if you
more
want, like,
decimal
10
places?
degrees.
Like that's what you like. You want this?
Yeah. Okay. I just was curious. Okay, so it's 2 point. Okay, and the difference between
Dude, you're the first
the
person to ever ask for that. Like this looks so visually unappealing. I can't make any sense of
Yeah,
this.
but all 3 of
Anyway,
those are equivalent, right? Like
yeah.
when we go down to the seconds,
I know. I work with that's how I would work it. I wouldn't
Gotcha.
work the degrees in second. You know what I'm saying? So I'm not
Sure,
familiar
sure.
with that. So
well, that's why we show all 3 equivalently all along, because we find that we like the degrees, minutes, seconds. That's what we can say. I've never heard another human say that they conceptualize it using decimal degrees.
Yeah, I'm a little disgusted.
I'm not refuting it. I'm just saying you're the first I've ever encountered. But that is why all 3 are up there. And the difference in like meters, you're saying you conceptualize decimal degrees easier than meters. Is that what you're saying?
no, then the degrees, minutes, seconds.
Right, but it's all describing the same amount of drop in meters, right? That's what we're
I
talking
know. I know.
Okay,
I know.
cool.
That gives me an idea of the precision. Okay, so it's just units
So
for me. So
got
I've
you.
been I wouldn't
Yeah,
would
so
working in degree. I've been working with degrees, minutes, seconds.
got you. So precision wise, we're looking at 1 arc second because Stellarium is records everything in 1 second intervals. So that translates to 1 arc minute of accuracy. So that's what we're looking at in terms of that. So if if that helps you.
So what place? Do you know what place the seconds would be in terms of decimal?
That's not how the conversion works. It's super that's not how it works at all.
It's 60, 60, 60. I know about how they came up with this, right? This is 60.
So
It's
you think
60,
the 100th
60,
decimal
60.
place equates to the seconds in a nice clean, like, no, that's not how the conversion works at all.
I mean, it's a raw conversion with just
Right.
60 and 60,
So-
right? Because 60, 60, and 60 degrees, minutes, seconds.
So check this out.
3600.
There's a converter on the spreadsheet as well. In the legend tab, you can convert degrees to decimal degrees and to your heart's content, and you could see all the decimal places there if you absolutely wanted to do that. But it doesn't change. Like having more decimal places doesn't change this year. So these are the set values here. So yeah, we can now proceed on.
For me, no, but you said the difference was 10 arc seconds, which is equivalent to how many degrees?
10 arc seconds.
You said the difference. The prediction for the globe was this, and the prediction for flat was this.
Yeah, 2 arc second difference for flat Earth, 10 arc second difference for what the globe predicted.
Arc minute?
Oh, I'm sorry, arc minute. Yes, thank you. Sorry,
So
both of those
0.4 degrees, or 0.04 degrees, or 0.18. That was the difference. That's a large difference.
Indubitably.
Okay. So that's what. Okay. Yeah.
That's a big problem.
But you don't have refraction in here, though, do you? Do you have standard refraction in here anywhere? Did you look at that?
Well, the thing
for
with
this instant-
the thing with the occlusions is that it's a physical process. So the refracted apparent image of the mountain is not going to block the starlight, and the refracted light is not going to be blocked by the apparent image. It's going to require a physical intersection point. So we reference the true position, which would be considered, the light source, and we consider the rise over the run for the mountain or whatever the globe would predict for the physical geometry, because without those two physically intersecting, there is no occlusion. So we have the calculations here for standard refraction, although they are not applied for this analysis here. We're doing strict raw geometry. But if you were so inclined, you could, I put the link in the spreadsheet at 20:57 past the hour there. But you can scroll all the way over to the end column here. And down here, I have celestial refraction, terrestrial refraction, all incorporated in there. So when like all the same things that we derived on the other, just doing the raw geometry, you could see the refracted variance down here. So the red one here is the refraction, celestial refraction, And then the one down here is terrestrial refraction, the pink one. So
What,
if
what
you,
about the raw angle, like we were just looking at, for the difference between the two,
Yeah.
your two calculations?
so terrestrial refraction adds like a little over one arc minute of refraction.
2 arc minutes, one. So it's like 7/6R broken down to 1 over each kilometer. It's like 2.1 arc seconds. So it comes out to 2 arc minutes total, but 2.1 something for this 50.7 kilometers. So it moves from 2 degrees 17 minutes to 2 degrees 19 minutes. Doesn't help at all, even if we were to allow it.
Okay, so it gets you closer, but it's just not getting you all the way there, right?
Yeah, and then there's also an additional problem too. So like we haven't really gone over this yet because this is kind of like advancing it a little bit. But you know how on a globe they say the sun setting, and what you're looking at is basically the after image of the sun setting because of refraction. Like the true position of the sun is already below the horizon.
Sure.
So like in this scenario here, there's what would happen is the amount of astronomical refraction applied to the star, if it worked 1-to-1 in the way that they say that it does for the sun to keep that after image up, what would happen is a star would it would like hit the mountain peak, like the visual star that we're seeing. It would hit the mountain peak and then it wouldn't get any lower. It would just linger right there as the true position starts to get lower behind the peak, and then it would disappear. But no stars like linger like that. That doesn't happen. So
I don't agree with that analysis.
well, that would conflict with the explanation that they give for sunsets. So like that's why
You're talking about a continuous process, so it's not beginning or ending, so there's no lag. There's just a process that happens.
well,
The
they're both
beginning and end.
they're both a continuous process though.
Yeah, so I mean, you're acting like basically, I don't know, that doesn't make any sense in my mind the way you describe it, because you're saying it's lag behind what?
It's looming. It would be lingering due to refraction. So like the same way that they say refraction keeps the after image of the sun above the horizon, allowing it to set into it, the star should linger because it's not being fully occluded yet, because it has to, like all that refraction that they ascribe to it's like 12 arc minutes of refraction there. It would have to get, the true position would have to get 12 arc minutes lower before it would get occluded. So it would loom.
I'm not sure I agree with that.
Yeah, it's a tough one. I'm gonna have to add some visuals, but like I'm just saying that even though like if you were to adjust an apparent position here or there, it doesn't actually like fix the issue mechanistically, because then there's still this amount of refraction that doesn't work in the 1-to-1 way that it would have to. The way that they say that like
Can
go
you
ahead.
guys hear me?
we can now.
Yeah, you know how the SunCalc website predicts the rising sun and the setting sun and the degrees at what it rises supposedly. Isn't that completely wrong? Because if in my opinion, when the sun is traveling through a very long distance through the atmosphere and there's a variety of temperatures everywhere over the surface of the earth, wouldn't that sun that is quote unquote rising be at a totally different position and what it really actually is? You understand what I'm saying with the whole sun calc thing, where they show the degrees of the sun when it's rising?
It would be off by 7/6 over R typically, which is standard atmospheric refraction. Like if it's on like a normal day, 76 degrees, not super hot, not super cold, kind of chill atmosphere. It
Yeah,
typically,
but sorry, go.
like I said, it's gonna be off by a little bit, and it's always not gonna be perfect.
Yeah, but that standard refraction is used in a short distance, like 8 miles, not I don't know, 500 miles that the sun is traveling through the atmosphere before it reaches your eyes, or more. 1,000 miles.
Well, yeah, I mean at the beginning, when the sun's setting, or in the evening, or I mean in the morning and the evening.
No, I'm talking
I
about.
mean, you're looking through a lot of atmosphere, yeah.
Yeah, I'm strictly talking about when it rises, like literally, like maybe 5 degrees off the horizon to 7 degrees. That's where the sun is at the densest part. Anyway, I just wanted to mention that. It's a little bit off topic, but I think that what they have in the sun calc thingy is exaggerated because it, in my opinion, it deviates the light a lot more than what it actually is.
Is it you taking these measurements yourself?
Shane, have you ever
No.
experienced any anomalies in sun calc? I think it's pretty accurate for the most part, isn't it?
Yeah, I'd like stellarium. I haven't found any instance where it's incorrect about anything.
Even at the rise, you know, when it's just like coming off of the horizon, and what is it going through from our eyes to the sun? Like how many miles is that? And in that goes through that atmosphere that we're in
Are you talking
before it
about
rises
you're talking
higher.
about the longest distance you can observe the sunrise over using sun calc? Is that what you're talking about?
No. Right when the sun is rising, right when it peaks over the horizon, that's when the sun is at the densest layer, right? And the lowest. From the sun to from the sun to my eyes. Isn't that when it's shouldn't that be like pretty deviated from what the actual position of the sun is? Because it's traveling through the densest medium, and that's why they say the sun is it doesn't match on any flat Earth model when it rises in Australia, for example. I don't know if you guys are understanding me or I'm not explaining it correctly.
No, we understand what you're saying. You're looking through the longest distance possible in that occasion. Because you're looking at an angle. I believe that's true. But you got to understand that the PSI reduces drastically as you move up on their surface. So, you know, the refraction is not going to be super dense as you move up and away from Earth, and the PSI gets lowered drastically.
Yeah, because what they say when it rises in Australia, it rises very south, and then when it goes over your head, it goes in an arc, almost the exact way that it should be, when it rises over like 30 degrees or something like that.
Well, there's
That's when
also
it's.
Sorry.
Oh, go ahead.
I was just going to say there's also stories that dusk lasts longer in the south for the opposing time of the year. There's no symmetry going on.
Well, can I just point out? I mean, I think I'm not sure if we're talking about flat Earth versus Gleason model. If you talk about Gleason model, that's ruled out by the fact that the sun sets in the south of west in the southern hemisphere and rises south of east. That's something that can't happen anywhere, I think, right, with the sun doing what it does. But in particular, of course, in Punta Arenas, the TFE guys saw the sun dip below the southern horizon. They could still see it due south, right, just below the horizon at midnight.
Yeah,
that doesn't
to be
rule
clear,
out a flat Earth.
And to
that
be
doesn't
clear,
rule out a flat Earth, but it rules out the Gleason model.
No, it rules out a conceptualization of mixing Newtonian physics with the apparent position of the sun. So where an observer sees the sun and how it moves is going to arc or anti-arc, which is a latitude dependent effect. We all see the sun individual to us, which is noted by the anti-corpuscular and corpuscular rays that we see and sunbeams that we see at a beach. It's all individual to us. Now, I know what you would say, right? But like that's the conflation of mixing Newtonian physics with it, like saying that the sun is a physical object. This is where it's at. It's like we have a quote unquote true position for it, and it does a circle around us. We perceive an arc, anti-arc, depending on where we're at latitude wise. I wouldn't say that it rules out the Gleason conceptualization of it. I would say that it rules out the aspect of us seeing like the physical sun, right? That you would have to then argue that it's an apparent position, which is true in both models. It is the apparent position. We see the apparent position in both models. So it's only the further belief of like beyond what the apparent position is. We know that it's, one astronomical unit away, which is 93 million, like that kind of thing. That's the only thing that separates the two and extends to what you believe is a different model than the AE model, which is based off of single observer observations and adding 15 degrees per hour to the positions of the bodies overhead. But anyway, go ahead and continue, lads.
Well, I would just encourage anybody to just look at the Gleason model, see what they think the sun would do. See how, I mean, in addition, of course, to the fact that the sun can't appear south of you ever in southern Australia, let alone set in the south. Unless you believe it's not physical. If you don't believe it's physical, then that's of course another whole thing. But in addition to that, there's just the fact that no flat Earth model will ever be able to predict sunset and sunrise times for the perfectly obvious reason that the sun doesn't set or rise on the flat Earth model. So I'll just point that out.
That's
Yeah,
ridiculous. That
well-
other dude put forth his
That's
his
past
predicted
ass
age,
stupid.
for the TFE or whatever. It's fine. That was my fault for listening to John. Sorry.
To the guy presenting, I'm curious if you acknowledge the how degrees, minutes, and seconds came about. Do you know, like historically, why that's used? Supposedly, we'll say supposedly historically.
Well, I don't know. Are you asking me?
to relate an
No,
angle
that's what
to
Gilda was
relate an
presenting.
angle to time, I would assume.
Yeah, as its ship travels and over the curve of the Earth, like a nautical mile is a fraction of the circumference of
It's
Earth.
only it's a unit of a circle. They recontextualize it historically to mean exactly the distance traveled in 1 arc minute in relative
There you go.
modernity. That's not really like the whole point of it. It really was just the unit of a measurement of a circle. So at its heart, it's just a ratio. And then they do define it, like we said, in modernity by defining with the circumference of the Earth, tying it to a specific distance traveled in 1 arc minute.
There you go. So do you not? So do you acknowledge that? So you do acknowledge that
That
that's
it's a unit of a
historically.
circle
Yeah,
and
but
a
do you
ratio?
do you
Sure.
acknowledge that it's the ratio of a circle? Like, because that's the
Well, a very
that
specific circle.
that's one that has 360 degrees in it. Like, dude, it's
No, one that has
Even more than
one that has a circumference of what is it? Is it 32,000? I forget what the circumference
oh,
is.
right,
Maybe
right.
23.
Yeah, but you get all of that though by multiplying out the path of the stars. So like what you can do is you could take the true position of the star. I forget how we did this, but if you look at the spreadsheet here, am I still screen sharing? Yes. So you could take the true position of the star here, and you could take the true position at the observer location, subtract that for 27 arc minutes, and then I forget the way you do it, but you multiply out the 27 arc minutes times the nautical miles, and it comes out to be the circumference of the Earth. Like all of this is just based off of objects in the sky moving at 15 degrees per hour, like the ratio of the circle. It's like it doesn't have anything to do with ground drop or whatever. Like it could just as equally be.
What do you mean?
It could just as equally be the arc of that a star makes as it moves. So
I don't believe it could be. It has to be a very specific ratio. And that ratio has to do with the circumference of the Earth.
Well,
it's very
check this out. Let me see if this helps you. So the true position of the star moves at 15 degrees per hour, which would follow the 60 nautical miles per degree, right? Dead on. The apparent position of the star that we see requires astronomical refraction corrections to keep it at the 60 nautical mile per degree ratio for its angle. So what they're doing is essentially saying, hey, this star is it's still being visible because the Earth's a globe, but it's being lifted up to make it look like it's flat, like the apparent position. So again, the circumference is based off of calculating, the return position of the stars with no refraction or interference or anything like that. And the apparent position, which is what the model is based upon for the 69 miles per degree to hold, isn't true for the apparent positions. If you were to multiply out the circumference based off of the apparent positions, it would be bigger than Earth's circumference, and it wouldn't follow the geometry properly. Like a day would be longer based off of that, and that's not what the case is. So it follows the 15 degree per hour geometry specifically for the true position. So it doesn't have to have any physical meaning at all for the ground. It's literally related to when's the star coming back. And and how it
Well, it
moves.
does if you're talking about global navigation. If you're talking about that's what we use in the skies and the seas. They use nautical miles
Well, yeah, so
specifically.
the definition of a nautical mile specifically is tied to the equatorial circumference. However, the equatorial circumference doesn't necessitate globe, right? It's the exact same on a flat Earth. Even on the Gleason's map, that circle is the same length in both depictions of that model. So even if you're gonna say that that length of that circle is not specific to globe or flat, either way, you'd have to differentiate. You'd have to go further south or north, either way, right?
Yeah, but the Tropic of Cancer then does necessitate a globe because it's
Well, yeah,
smaller
but we
than the
started with
equator,
the
and it can't
definition of
be
a
on any.
nautical mile.
But on
This
any flat Earth conception, it couldn't be.
The objection somehow was a nautical mile. A nautical mile is the only unit of metric measurement that is actually defined in physical terms in relation to the Earth. All other units of measurement are ratios of this, right? So that's why it's significant, but we argue that all the time. And I don't know how that was gonna. I don't know how we got to the definition of decimal degrees to nautical mile. To was any of this Celthio
Yeah,
arguments? Or we
yeah,
just
it
on
was
the
to
same
relate
one?
ships traveling over a ball curve or whatever. Like it was a feigned attempt at that. But to bring it back here, we got stars being occluded by mountains that are higher in elevation than what the globe predicts. And we only spent the analysis tonight on Pikes Peak, but we do have other peaks. We've got an entire data set, a range of things to go through. But we've been going kind of long tonight, and I am moving tomorrow. Got to hop on the old plane tomorrow. So we are going to wrap up here rather shortly. If anyone has any closing thoughts or or a question or something, we can get through that real quick, and then we're going to wrap.
Here's wishing you a safe journey.
Thank you, sir. All right. I don't hear anyone talking, and I don't think I have everyone muted. So I think
I mean, I will ask you one more question. If
Okay.
you and
Yeah, go
if
ahead.
you have time to answer, go ahead. So do you acknowledge that if I need to know your location, I can give you give me your GPS coordinates, right?
Absolutely.
And that's a unique. Okay. So I don't know how I don't understand how if you acknowledge that, you can't acknowledge the system. Like you're basically acknowledging the globe Earth. If you acknowledge that GPS works, a global positioning system, that your physical location on Earth is dictated by two basically degrees from to a radius, right? I don't understand how you can acknowledge that and not acknowledge that the Earth is a globe. I don't understand that.
Well, I don't think that the GPS system or satellites are free falling around us. I think they're circling above us by some mechanism that I don't know how they work per se, but I think that that's how they work. And in terms of the timing corrections that they make, so the circumference of the Earth is like, was it like 21,000 or whatever it is, and the orbit of the satellites is the same. So if you flip that, the timing correction is like literally the same as if it was at that altitude. So if it was at a lower altitude, but still traveling around that same circumference, the timing corrections that they could make would produce, like it would be compatible with the coordinate system as presented to us to make you think that it's a globe. And it would give you, coordinates that are latitude and longitude dependent, which are positions that are defined by positions of where the stars once were. So it's just kind of going back to the same exact system. And in addition to that, there are back-end timing corrections that occur on board the satellite carrying the clocks. And if they're adjusting time on the back end, then nothing for certain can be said about what we receive as the receiver, because everything is already going to be compatible with the coordinate system that it's referencing. So yeah, I wouldn't
think it's basically buried in the math somewhere. There's some trickery going on, essentially.
Yeah, I could actually link the equivalent. I'll link you this if you want to check it out, but it's the equivalence of the Sagnac effect, accounting for it as if it's completing the circumference of the Earth, just doing a circle above us versus doing a loop with an altitude of 20,000 kilometers, comes out to be the exact same correction. So like, in my mind, that's pretty good evidence.
That's a crazy coincidence, though.
I mean, is it a coincidence? You know what I'm saying? You know what I'm saying, brother?
But well, that's the thing is that we're talking about real world things here, right? So
I know.
I could just technically tell you're sharp, and I wanted to ask you that specific question because that is just such a doozy, man. And I know you. I can tell you understand it. So I appreciate the answer.
Yeah, no worries. I sent the links for the SAGNEC stuff. It's at 2119 past the hour for GPS. Give that a read. When you get down to the bottom one on the second page, it starts covering the SAGNEC effect. And when it gets to the orbital radius versus the circumference, like the equivalence there is profound. And if they have the freedom to make what they call meridian corrections, which means when at any time a satellite passes two D GPS stations, it sends timing offsets for it to adjust the onboard clock to keep it in sync with UTC time, which keeps it in sync to latitude and longitude. So as they do that, like if they have the freedom to do that, then like what you're getting isn't like raw independent globe math or whatever. You know what I mean? It's like it's fit to be exactly what they would need it to be.
Except you have the small problem that's irrefutable that you could have two GPS receivers that are hundreds of miles apart that are within the same horizon of the same GPS satellites. You could look at the data from those satellites and see that they're receiving precisely the same timing data, which they use to
Yeah.
trilaterate their
Yeah.
position, and it trilaterates an accurate position in within a three-dimensional coordinate system that is then plotted over the WGS 84 that accurately shows their longitude and elevation, which would not be possible on a flat Earth if they're receiving the same data, which we know that they are because you can look at the logs and see that they
You
receive
said our point, but you
precisely
conclude
the
the
same
globe.
data.
That's
No,
exactly
there's no explanation for that.
That exactly was the explanation. This satellite is sending out signals that are already corrected. So when two people get the information, it's accurate for them. That's exactly our point.
In the ellipsoid WGS 84 current model, yes, self-correcting, internally consistent. Absolutely, that's exactly our position.
No, there's no
I like that.
mathematical. There's no mathematical.
And then
There's
also
no mathematical way to show that. And that's why you
so
guys don't have any.
so
You guys don't have
so
a proof of how that could actually be
well,
done
before
mathematically.
you interrupt and tell me what I don't have proof of, I do have proof that they make meridian corrections on the back end, and that when you try to analyze the highest level of available raw data, you know, like literally going to the GPS station in Colorado to get the data, it's already pre-corrected. So there is no civilian publicly available data that isn't already pre-corrected. So I don't need to show anything else, right? It's already at the highest level that's publicly available to us. It's already corrected. They've already made timing adjustments. And on top of that, there's meridian corrections, which nobody knows what those are.
We can guess,
So,
though, right?
so just the fact that the meridian correction is already canonized as a function of how they keep time to make GPS time work, like that's it. That's exactly how two people can get the signal that's being cooked and it worked out because it's already corrected on the back end. Like I don't understand why you guys say that, and then like that's our point, dude.
Well, let's think about this logically, though, Alan. Right? If you have, let's say, the minimum number of GPS satellites to trilaterate your position, right? Which is, I believe, it's 4 satellites on your above your horizon, right? And they're transmitting time and location data that all the receivers that are within that that can receive that signal within their horizon that can see those satellites, they're all getting that same data, right? You can see it in the logs of those receivers and see that they are receiving the same identical data at the same moment in time. And then they use that data to then trilaterate their position. And there's no possible way to somehow embed into the way the system works a way that they could be receiving coordinate data, that they could be receiving data in a way that would somehow still accurately allow them to plot their location in 3-dimensional space. Yet somehow it's making it look like a flat. It's making it look like they're plotting their position on a sphere, on the surface of a sphere as or a spheroid, as opposed to on a flat plane. There's just no way to do that mathematically. If you think about it logically, how could they do that? How could they trilaterate themselves that way? It's not possible because there's no mathematical way to do that. It's just a ridiculous assertion.
Well, you say it's a ridiculous assertion, but half of what you said is half of that was our, we agree. And the reason that it works is through timing corrections. The mechanism for that explicitly is timing corrections. GPS is a timing interval system. It derives distances based off of timing intervals, when the signal was sent, when the signal was received. Now, if the location of the object of which it is being sent from is at a different altitude, but it's being corrected on the back end, then the signals that it sends out for it are going to be modulated in a way that when they come out, it's going to be referencing the altitude for which they're should be at, or whatever, on the coordinate system. So it's literally just a math function to flip the two, to have the circumference, that's orbital circumference, be its altitude. And keeping the system in alignment requires corrections that happened again on the back end that we're not even aware about. So when you say that it's impossible, et cetera, when you say, hold on a second, it sounds like you're talking over me, and that would be extremely rude if you were to start talking over me while I was about to wrap up what I was saying. So now I have to take a second to collect my thoughts after that. So give me 1 second, sir.
Come on, Jake.
So again, if you were correcting on the back end, you wouldn't have any way to know about that. And two gentlemen named Wolf and Pettit in 2000 went to get some raw GPS data from Colorado to analyze the isotropy of the speed of light. And what they found was that those were already corrected. And also, in addition to that, there are, actually, I'm not even going to talk about that. We'll go ahead and say your closing thoughts or whatever. And then we're going to wrap up for realsies. I'll share 1
Live on
second.
a flat Earth? Did they do that?
Sorry.
Jake, can you be
sorry,
for
repeat
real,
that again.
please?
Did Wolf and Pettit, do they think we live on a flat Earth?
Such a joke.
All right. So guys, that was his closing thoughts. Did they think
No, I just want to answer. Are you going to answer the question?
No. Jake, that was Jake, that was your closing thoughts. So did they think that? I don't know. We'll have to ask them. So with that said, we're going to go ahead and wrap up we're going to go ahead and wrap up Cell Theo update 22. Thanks everyone for participating. And if there's any questions about the math and whatnot, send them over and we'll do our best to make relatable diagrams and get that sorted out. See you guys on the next one. Let's see, for Ether Cause events, there's going to be a special premiere regarding the celestial theodolite and eclipses. So make sure you stay tuned for that, for episode 104 on Ether Cause. That'll be on October 7th. So we're going to be doing a big premiere for that night. All right. See you guys next week.